There it goes. Hey, welcome to this first video lesson on stoichiometry. So this is going to be sort of the intro, and to intro this, I'm just going to work out a problem for you, explain every step of the way and what we're doing, and try to break it down as much as possible. But here's the situation. We have 255 grams of octane. And so this is the formula for octane, C8, 8H18, 8H18, sorry, I can't speak, and it's combusted. And so then we also learned that we have 1,510 grams of oxygen for that combustion. So when we remember from reactions, a combustion reaction means combining with O2. And so it's got to, anytime you combine with O2, we have a combustion reaction. So O2 has to be one of the reactants. So, so the first part is to write and balance the equation. All right, so let's go ahead and do that. Right here, we have C8. This is our octane. I'm going to bring that down here. C8, 8H18. Can't say it still. And combusted, so we know that's going to be combining with O2. So what does that produce? Well, anytime you combust what's called a hydrocarbon, something with carbon and hydrogen, you always get the same products. It's always CO2 and water. And so that's something to look for. Typical combustion reactions most combustion reactions that you'll ever see actually end up combusting with these kind of hydrocarbons. And so this is often the products. When they say combustion, you can almost immediately assume you're going to get these two products right here. Now, with this equation, we do have to balance it. And so balancing the equation is, this particular one is a little bit tricky, but most of them are more simple than this one. But I picked a little bit more difficult one so you can see the process, and it's not that hard. And so, let's take a look at this. So over here we have 8 carbon, and over here we have 2. So I'm going to use a different color so that I can show you what I'm doing here. So what I'm going to do then is I want to match these up on either side. So if I have 8 carbon here, I need to have 8 carbon right here. And so then I go to my next one. Now the trick to balancing equations is to leave the oxygen for last. The reason for that is that if you notice over here it's in 2 compounds, and over here it's only in 1. And so at the very end we can reconcile it with this 1. But that often happens with oxygen. It splits up into many different things, and so you want to leave it to the end because oftentimes it can actually work itself out. Alright, so now let's take a look at what we've got. Now we have 18 hydrogen over here, so hydrogen 18. So we're definitely going to have to put a 9 right here. Okay, so 8 carbon, 18 hydrogen, 18 hydrogen. Now let's look at our oxygen. So 8 times 2 is 16, and 16 plus 9, now this is going to be a problem, right? Because 16 plus 9 is 25, and I cannot make this 25. So what am I going to do? Because I do have to have whole numbers here for the balancing equation. And so here's the trick. If you ever come across a situation where there's an odd number on one side, even number on the other side of oxygen, you just double everything you've done so far. So I worked on this one. I originally had a 1 there. And so I'm going to double that. So doubling that 1 brings that to 2. I'm going to double this one, brings that to 16. And I'm going to double that one, brings that to 18. Alright, so now let's count out my oxygen. So I have 32 plus 18. 32 plus 18 is going to be 50, right? So then that's going to leave me with a 25 right here. Okay, so there's my balanced chemical reaction right there, and so that's kind of like your main starting point is to be able to balance the chemical reaction and write it out properly. If you can't do that, you have troubles. But it's not a difficult thing. And so do make sure you spend the time to get that correct. And so the next question asks us, what is the limiting reactant? So the idea of a limiting reactant is that it runs out before the other one. So we have a certain mass of octane that we put in. I'm just going to go ahead and write that under here, 255 grams of octane, right? And we also have a certain mass of oxygen, 1,510 grams of oxygen. And so the idea is that if you look at the balanced equation, I have 2 moles of this to every 25 moles of this. So I need a whole lot more of this than I do this. I'm going to try to make that into a better 5 for you. Beauty. Okay, so so what we need to know is, will the octane run out first or will the oxygen run out first? And so the only way to do that is to take this mass and convert it to moles. And that's really the first step you have in any stoichiometry problem after you balance the equation, is taking whatever they give you and putting it all into moles, because the balanced equation is a mole ratio. This is amount of moles to moles, not grams to grams, but moles to moles. Because when we convert to moles, we take the molar mass of a thing and we make it essentially into a number. Moles is just a number. And when it becomes that number, everything is calculated based off the same number, so then they're comparable. But masses are not comparable. Octane is much heavier than oxygen, so the mass of this is not really comparable. So how do I convert mass to moles? Well, to convert mass to moles, you divide the mass given by the molar mass of the compound. So to find the molar mass of the compound, what you're going to have to do is you're going to have to add up all the elements that are in it. Now when you find that molar mass, you ignore the coefficient in front, because that's just telling you a mole ratio of what you need. It doesn't change the mass of the compound. This is just telling you how many of them you have. And so so my compound's going to weigh 8 carbons and 18 hydrogens. So 8 carbons and 18 hydrogens, if you add that up, 12 times 8 plus 18 is going to give you 114. And that's grams for 1 mole. So the idea is that once I have 114 grams, I have a 1 mole. So 114 grams is the weight of this that it's going to take to get 6.02 times 10 to the 23rd molecules of this. And then I do the same thing with O2. Now O2, I just have 2 oxygens, so that one's going to weigh a bit less. Like I said, this is going to weigh much more. And we find that out now. So 2 oxygens is 32, because each oxygen is 16. And remember, I ignore the number in front because that's just telling me my molar ratio when I'm calculating molar mass. So to turn mass into turn mass into moles, you divide by the molar mass of the compound by adding up the individual elements. And then the next thing you're going to do is you're going to actually use these things. So then you're going to use those things to compare. So when we divide this out, we find that 255 divided by 114 is going to equal 2.23 moles. I'm going to erase this out of here. It's kind of getting in the way. And we'll get back to that later. So 2.23 moles, when I divide this out, 1510 divided by 32, I get 47.19 moles. Okay, so now here's the question. Which one is going to run out first? Well, the ratio is 2 to 25, and that has to match what I have here. So there's 2 things you could do. You could take this one and you could take this one and multiply it by 12.5, or you could take this one and divide it by that. But the idea is you have to get it into a molar ratio that matches. So so let's see what we got. So 2 to 25 is the same as saying 1 to 12.5, right? So let's go ahead and say, so this one here has to be 12.5 times bigger than this one here. And so if I take 2.23 and multiply it by 12.5, I get 27.9 moles. And so hopefully you followed me on what I did there. But all I did was I said this ratio has to be 2 to 25, and I turned that into whole numbers. I said 2 to 25 is the same as 1 to 12.5, and so this if I multiply that by 12.5, I get this. Now this one right here. To find something that's 12 point times something that's 12 point times smaller, I could divide that by 12.5. So 47.19 divided by 12.5 is going to actually give me 3.77. And so this would have to be 3.77. If I was going to use all of this, I'd have to have 3.77 of this to match up with the 2 to 25 ratio. And I simply don't have 3.77. I have 2.23, so I cannot use this divided by 12.5. And so then here's my new moles. So the idea is that this one is going to have more than enough, and then this one is going to get used up first. So my limiting reactant is octane. So I can write that over here. Let me go ahead and put that in pink. That'd be fun. So C8, 8H, 8, bleh. Okay, C8H, 18. I can speak. That's awesome. So the next question is, which reactant is in excess? Well, we found out that we're going to have too much oxygen. So the O2 is my excess reactant. And then amount left. We'll go ahead and add that. Amount is left. I erased that over there. And how much is left? Well, I find out that I can only use 27.9 moles of this original amount. So if I subtract that, my 47.19, and I subtract my amount that I can use, my 27.9, I actually end up with 19.29 moles. Right? So my 19.2 moles, that's how much excess. Well, to find out how much mass that is, to go from moles to mass, you do the opposite of what you did to go from mass to moles. So you'd multiply by the molar mass, because the idea of this is like every 19 moles equals 32 grams. So I want to know how many, or every 1 mole equals 32 grams. So I have 19 of them. So I'm going to have 19.29 times 32 grams per mole, which gives me 617.28 grams extra. So this is just excess right here. And so I would put that right here. That's my 617.28 grams excess. All right, and so then the last question we have to work on is how many grams of water are formed? Well, all I got to do is look at my ratio. So my ratio here is 2 to 18, which is the same as saying 1 to 9, right? So 2 to 18 is 1 to 9. So what I know is that water is 9 times larger than octane. Now, why would I use octane? Because octane is my limiting. Once you find out your limiting reactant, it is the one that determines everything else, because once it runs out, the reaction stops. So you wouldn't want to use this, because this, we didn't use all of that. You could use this, that would work, but that number was determined from this number. So your best practice is to use your limiting to figure out all the other ones. So 2.23 times 9 equals 20.07 moles. And how do I convert that to mass? Well, same way I did down here. When you're going from moles to mass, you multiply by the molar mass of the compound. So if I'm multiplying by the molar mass, every single 1 mole of oxygen equals the weight of 2 hydrogens and or every single mole of water, sorry, equals the amount of 2 hydrogens plus 1 oxygen. So this is 2, and this is 16, so I have a total of 18. So 18 grams per mole. So if I have 18 grams, I'm going to have 1 mole. So notice I have 20 moles. So it's going to be 20 times 18, or 20.07. 20.07 times 18. So my final answer is 25.2 grams of H2O formed. So now what's kind of important is that with all of your final answers, it is important to look at your significant digits. So I have 3 significant digits with this data, and I have 3 with this data. And so all of my answers have to be limited to 3. So I should actually change this back down to 617 grams right there as that final answer. And this one is good at 25.2. Alright, there we go. So we have done a stoichiometry problem using the combustion of octane and finding out which one was limiting, which one was excess, how much excess, and then how much product was formed. It'd be easy enough to figure out how much CO2 too, because it is 8 times larger than this, so you just multiply that times 8 and then multiply by the molar mass. So either one would be a simple thing to find. So hopefully that helped, and there'll be more to come.